Hello, lovely humans. Jen Fox back here. In this episode of Math Mondays, we are finally getting into electrodynamics. Ooh, yeah. Wait, what have we been doing this whole time? Electrostatics, my friends, where the charges might move, but then they reach an equilibrium and they hang out, and then we come in with our math and our measuring apparatuses, and we're like, what is going on? So in electrodynamics, we're dealing with moving charges. In this video, this introduction to Ohm's law, I'm going to break it into two parts. In part one, we will build up an understanding of the basic terms that we are talking about when we're dealing with moving charges, things like electric current, charged or current density, that sort of thing. And then in part two, we will look at two example problems which will help us get to the pure version of Ohm's law to the more classic version of Ohm's law, V equals IR. Yeah. All right. So let's get started. Like I said, with electrodynamics, we're dealing with moving charges, aka we knock the charges and they go off and start flowing through a particular material. The speed that these charges move depends on the material, which makes sense, right? Because if we are working in a conductor and we give the charges a little push, they're probably going to go faster, or they'll run into fewer obstacles than if we give them a push in an insulating material. In general, we can say, and we know, that the current density J, this is a vector with its little hat, is proportional to the little pushing force. I'm pretending like I'm flicking charges. That's not exactly how it works, but that's okay. So this is the constant of proportionality. And so this is called the conductivity. I have a hard time spelling this word on the chalkboard. The conductivity. And this is a property of the material that the charges are flowing through. For metals are really good conductors. They do not resist the flow of charges. And so for a perfect conductor, we could assume that the conductivity is infinite. For insulating materials, this value is going to be much, much lower. And so then we might start to ask, okay, well, if we want to figure out the current density, where do we start from? Well, we need to know something about the force that's causing these charges to move. Maybe my finger flicks a few of them, or maybe I hire a bunch of tiny little ants to pull the charges along. Yeah, maybe. But most of the time in electrodynamics, what we're dealing with is an electromagnetic force that causes these charges to move. I attach a battery to a circuit, and that has a potential difference, and so it is an electromagnetic force that causes the charges to move around the circuit. Or maybe I have a magnet and I wave it through a coil of wire. That is an electromagnetic force that causes the charges to move. Yay! I did skip magnetism because I wanted to get to Ohm's law, but if you want me to go back and cover some of those topics, let me know. Very quickly, a moving magnetic field generates an electric field and vice versa. TLDR. Now we know magnetism. But when we're dealing with an electromagnetic force, we have those two parts. We have an electric field and a magnetic field. And so if we plug that into this equation, we get the electric field plus the speed of the charges times cross, not just times, the cross product with the magnetic field, because this is what would generate the equivalent electric field to move those charges. And in reality, so this is the full form of Ohm's law, but in general, you can ignore this because the velocity is often very, very small. V, we can assume that it's close to zero. And so we can get the charge density is just proportional to the electric field. Hey, what's up? This is Ohm's law. Haha. Wait a second. That doesn't look like the Ohm's law that you're probably familiar with. We'll get there. Don't worry. But I think that it's important to understand that this is kind of like the starting point for the more familiar form of Ohm's law. And really what it's saying is that the current density is equal to the conductivity of the material, basically how easily that material allows charges to flow through it, times the electric field, the force that made them move. And that makes a lot of sense. The force causes an action, and that action is propagated through a material. Pretty cool. So you actually can look up the values of conductivity. The one last thing that I'll say is that you might also see the resistivity, which is 1 over sigma. It's kind of confusing because this is not charge density. This is resistivity, which is just flipped. Cool. Okay. The other thing you might be asking is like, wait a second, if we're talking about a metal or a conductive material, didn't we say in electrostatics that the electric field inside a conductor is 0? Yeah, great memory. Haha. So that's actually totally fine, because if we assume that we have a perfect conductor and we solve for the electric field, we're going to get the current density divided by the conductivity, and if we assume this to be infinity, this will actually equal 0. There you go. No problem. And actually, this is really cool because this is why we can assume wires in a circuit are equipotential at both ends. In other words, we can assume that the current flowing into a wire is the same as the current flowing out of that wire. Seems like a very basic assumption, but it is really, really powerful. It's not true in reality, but it's close enough that we can assume that, especially when we're talking about adding in other circuit components like resistors or capacitors or sensors and things like that that really do affect the current density because they have a different conductivity. And resistors, in fact, are made of different types of material, like ceramic, that have a much lower conductivity or much higher resistivity. So they resist the flow of electricity much more than wires. Okay, cool. So that is the general form of Ohm's law. And in part 2, we'll do some example problems. Yay! I'll see you in part 2.